Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on impedance matching. Okay, so this video is actually a request from one of you guys through the comment. Okay, actually someone suggests me to discuss on multiple quarter wave transformer. Okay, so before I go into the discussion how to design a multiple quarter wave transformer, okay, I'd like to start off when we actually need this multiple quarter wave transformer. Earlier on, I have done this part 11 series. I have done how to design a quarter wave transformer. So for this video, I'm going to do a quick comparison between a quarter wave transformer and also multiple quarter wave transformer. What will be the advantage? What will be the disadvantage? Why we need to have multiple quarter wave transformer? So all this will be the objective of this video. This will be the part 12 series discussion on impedance matching. So guys, if you're keen to know more about impedance matching, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on impedance matching. This is my email. If you have any question regards on this discussion, please drop me an email. Or maybe I strongly suggest you guys to ask your question through the comment. Okay, because I hardly check this email. So basically, if you want a faster response, I strongly recommend you to ask your question through comment, or maybe also give me some input how to improve the quality of this channel through the comment. Once again, thank you so much for strong support. Before I continue, I'd like to urge you guys to help this channel by like this video. When more of you guys actually like this video will have a better chances to reach up to a larger audience. So guys, help me by like this video. For those who are new to this channel, please consider to subscribe to this channel. Last but not least, please remember to turn on your notification bell in order to receive more information from this channel. Once again, thank you so much for strong support. Okay, let's quickly understand the key difference between multiple quarter wave transformer and also a quarter wave transformer. For a quarter wave transformer, it's actually a very straightforward and variable circuit for aligning a real load impedance with a transmission line. So in short, when we actually want to implement this quarter wave transformer, the key idea is to match the load impedance. Okay, basically the load impedance must be real. For example, 50 ohm, 10 ohm, 100 ohm, etc. And then basically the key idea is to match to a transmission line. So therefore, we want to use this quarter wave transformer in order to do this impedance matching. Another advantage of the quarter wave transformer, it is ability to be expanded into multiple section design systematically. Okay, so which means that I can have a synthesis design. Okay, how to design from a quarter wave to a multiple section quarter wave transformer. When only a narrow band impedance matching is necessary, a single section transformer may be adequate. Okay, which means that if let's say I just need a very narrow band of impedance matching, okay, or maybe I should say that the bandwidth to do impedance matching is very narrow. Hence, okay, a single section transformer definitely will be enough. However, for application that demand a broader bandwidth than what a single wavelength section can actually offer, then multiple section transformer become essential. Okay, so there's no way I can do an impedance transformer, let's say with a broad bandwidth. So therefore, in order to have a broader bandwidth, I need to implement this with multiple quarter wave section in order to do this impedance matching. Okay, in this discussion, I will explore two methods. Okay, so basically these two methods will be on my next few video. Okay, how to design this multiple section quarter wave transformer. Okay, so basically this method can be synthesized. Okay, which means that I will have a clear design rule how to design this multiple section quarter wave transformer. In short, over here there are two methods. Okay, one is a binomial multi-section matching transformer, Another one will be using this Chebyshev multiple section matching transformer. Okay, this video, unfortunately, due to the shortage of time, I probably cannot discuss these two, but on the next two video, okay, I will discuss the binomial, and then next will be the Chebyshev. Okay, so basically stay tuned if you want to get more information on this multiple quarter wave transformer. Let's quickly understand, okay, the key difference between a quarter wave transformer and also multiple quarter wave transformer. Okay, so in short, this you can imagine that this will be frequency. Okay, let's make it simple. This will be frequency. This will be, let's say, S11. Okay, so basically S11 here. So this is actually we call the maximum reflection coefficient. Okay, maybe you can imagine that this is a number. For example, let's say this is S11. For example, anything 10. Okay, will be considered matched. So anything that, imagine this will be 10 dB. So anything at 10, I consider this part will be well matched. Okay, I guess you understand what I want to say. So basically, this can be also 15 dB, etc. It depends on how stringent you want. So for example, most of the case, we actually take this as 10 dB. Just imagine this axis will be S11. So basically, for this bandwidth, okay, so they are actually so-called matched to this frequency, okay, which means that the impedance matching basically will be matched at this frequency, having the bandwidth from here to here. Then this is actually for a quarter wave transformer. Okay, so basically this diagram actually show a approximate behavior of the reflection coefficient magnitude for a single session quarter wave transformer, basically operating near its design frequency. You can see from here, I will say that this is considered a pretty narrow bandwidth. Okay, next. Okay, so from here will be the next discussion. Okay, so basically this will be the reflection coefficient magnitude, okay, versus the frequency for a single session quarter wave matching transformer with various load mismatch. Okay, so basically what this means that you can see that the ratio ZL over Z0 will be equals to 10. Okay, ZL over Z0 will be equals to 4, and ZL over Z0 is equals to 2. Okay, so over here you can see that, okay, when this number is large, which means that the value for this ZL and Z0 is drastically different, then I will have a narrow band. Okay, you can see over here, then I will have a narrow band of matching. Okay, so basically, if this ZL over Z0 is a big number, then I will actually has a narrow band. As you can see from here, when ZL, Z0 change from 10 to 4, okay, you can see that the bandwidth actually increase. Okay, you can see that the bandwidth increase, and further, okay, let's say this ZL over Z0 ratio become 2, you can also see that the bandwidth further increase. So from here, you can see that the higher mismatch between ZL and Z0, okay, basically the higher, which means that the higher difference, then it will be narrow band. And if let's say this ZL is almost equal to Z0, then I will have a wide or broader bandwidth to do this impedance matching. Okay, so I hope this is clear. So basically, in short, okay, if you want to have a very high bandwidth, okay, so basically what you need to do is you need to match this ZL and Z0. Okay, the value cannot be that far away. So basically, when they are not that far away, I actually can have a higher bandwidth, as you can see from this solution here. Next, okay, what I'm going to go through will be the reflection coefficient magnitude versus the frequency for multiple section. Okay, so basically, for this case, I will use this binomial matching transformer first. Okay, so over here, I fixed my ZL, I fixed my Z0, but over here, you can see that what I didn't fix will be the number of quarter wave transformer. So basically, for this n equals to 1, which means that I'm going to have 1 quarter wave transformer, n equals to 2 is 2 quarter wave transformer, and etc. And again, from here, I draw a very quick conclusion. Okay, when I actually has a quarter wave transformer, okay, it will be so-called narrow band. And when n actually increase, you can see that the bandwidth also increase. And when the n increases to 3, you can see that the bandwidth is further increased. So in short, okay, if you want to do impedance matching for a broader bandwidth or for a wider bandwidth, then I will strongly encourage you to use more quarter wave transformer. In short, okay, the more multiple section of quarter wave transformer, the wider bandwidth that you actually can do for this impedance matching. Okay, so next, Okay, before I continue to the next example, okay, so guys, help me by like this video, and if you have learned something from this video, please consider to subscribe to this channel. Okay, let's come into a quick example. Okay, the key thing, I have done this example in so-called part 11 series. Okay, but I have not really discussed on the percentage of bandwidth that is actually so-called matched. So therefore, I like to do another example in terms of discussing mainly on the percentage of bandwidth that actually will do this impedance matching. Okay, so this is something that I never so-called discussed on part 11 series. So I plan to use this opportunity to enhance the explanation of a quarter wave transformer, basically target on in terms of the percentage of the bandwidth that is matched. Let's come to this example. Okay, so design a single section quarter wave matching transformer to match a 10 ohm load to a 50 ohm transmission line. Okay, so basically this will be the 10 ohm loads to a 50 ohm transmission line. So basically this will be the impedance transformer. Okay, they are actually sitting in between the load and the transmission line, as I mentioned earlier on. Okay, so basically I need to match them at 3 gigahertz. Okay, I need to determine the percentage of bandwidth for which the VSWR is basically less than or equals to 1.5. Okay, so basically this is my question. Okay, I will quickly explain how can we actually design this single session quarter wave matching transformer. Okay, so if you still remember on the part 11 series discussion, I somehow have derived and show you we need this so-called characteristic impedance of the quarter wave matching transformer. So basically this will be the Z1, which sit in between the load and also the transmission line. So this is where the section of the impedance transformer, the length of the transmission line will be quarter wave length. Now I need to find out what will be the impedance in order to do this impedance matching. So basically I have explained this formula. So from here you can see that Z0, which is the transmission line, is 50 ohm. The load is 10, so therefore from here I can compute that Z1 is equal to 22.36. So in short, okay, the characteristics impedance of this Z1 need to be 22.36, and the length, let's say, of this impedance matching need to be a quarter wavelength with respect to 3 gigahertz. Then I will have this impedance matching. Okay, so like I mentioned earlier on this video, I want to concentrate on the percentage of bandwidth that is successfully matched, which I have not discussed on my part 11 series. Okay, so let's quickly do this. Okay, so basically this is the maximum reflection coefficient. Okay, so the formula to calculate the maximum reflection coefficient will be from this equation, which is the VSWR minus 1, VSWR plus 1. So from the question is given to us, the VSWR is 1.5. So I can easily calculate that the maximum reflection coefficient will be equal to 0.2. Okay, so next I need to calculate the fractional bandwidth that will be matched. How much will be matched? Okay, so this will be the formula here. So basically, in short, I don't want to go into so much detail. Okay, so for this video, I just want to use the formula to design the quarter wavelength transformer. So basically, this will show how much fractional bandwidth that will be matched. So basically, you just need to apply this formula. Okay, you can see that everything all go the same. So basically, this is what I have calculated from here, which is 0.2. Okay, 1 minus 0.2 squared here. So basically, this will be Z0. Z0 will be the characteristic impedance of the so-called of the line. So basically, it's given in the question, okay, which is 50 ohm. Okay, so basically, I think this 50 ohm, and then basically for ZL, okay, will be equals to 10 ohm. So from here, I can compute that, okay, basically for this fractional bandwidth will be equals to 0.29 or 29%. Okay, which means that, for example, for this case here, this is a single session here. So which means that the bandwidth is 29%. Okay, so basically with this, I'd like to end my discussion. Please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.